Okay, good afternoon all. Now, maybe around 2:15, I'll start the class because right now I just concluded my class in the other section. So a little bit tired, no doubt. So we'll start the class something around 2:20, and in that class I'll play the video for chapter number 27. Obviously, that video will give you some good idea about this entire chapter. We'll at least cover two or three number of videos, and once you are comfortable with this video, then in the class you will be much more comfortable because this will give you a good idea about this chapter. So let us please be online. We'll meet again at 2:20. Let me just have my lunch. Okay. But you people please be online.
Yes, sir.
Okay. So are you all ready?
Yes, sir.
Okay, fine. So right now I'll start with I'll play back that video. Just go through it. During that course, once the video stops, then we'll have some little bit of discussion if you are having any sort of doubt. Now the main purpose of this video is that at least you try to see what is actually going to be covered in the theory class. Make up your mind what we need to study, what you need to understand, or just have a look at this. And obviously, you're as usual in the class. I'll be discussing all this in detail in PowerPoint. Just have a look because this way itself I taught your previous your seniors a year back when the pandemic started. I started preparing these videos because during that time we were not advised to go for this PowerPoint presentation. And truly speaking, the students loved it because that was something which involved both the teacher and the student as well, particularly when I was writing the equations and other things. The students were having a lot of doubt, they were having instantly. So at that instant only, I used to stop the video and clear it. So let me see, just go through this. Okay, for the timing, since I will be going for a change in the setting of the audio, so I can my voice will not be audible to you all. So once the video is complete, then only you will ask me your doubt. Okay, dear students. Okay, let me tell you one another thing. The voice may be a little bit low in loudness. So if you are having your earplugs and audio system, then use that thing so that at least it will amplify the my loudness and you can enjoy it. And please note that during this time I cannot communicate with you because I will be changing the settings. Uh, Only one chat I will do to ensure that you people are listening it. Fine. Today we are going to study a chapter, new chapter, that is chapter number 27 on magnetic fields and magnetic forces. Before that, let me
just have a small comparison with that of electric field. Now, in case of electric field, it is represented by a symbol E vector. Now, E is a vector quantity. It is known as electric field, or as I told you in the class, that it is also known as electric field strength or electric field intensity. All of these refers to the same thing. Similarly, in case of magnetic field, we represent that magnetic field by the symbol B vector. B is also a vector quantity. So it is also known as magnetic field or magnetic field strength or intensity. Now, in case of electric field, the main source of electric field is either a single sorry, either it is a sorry, either it is a single charge, or it is a charged body. But in case of magnetic field, the case is not same. In this case, we don't have a, as you all know in your school, you have studied that usually a magnet is always going to have a north pole and south pole. Now it is next to impossible to isolate this north pole with that of the south pole. And therefore, there is no case of a single pole which is going to create a magnetic field. We will always have a magnet with a north and south pole. So this is the major difference between the sources associated with electric field and magnetic field. So what are the different sources of magnetic field, that we will cover in the next chapter, but right now it is highly essential to tell you that the main sources are, as you all know, is a permanent magnet. Permanent magnet like this. It may be a bar magnet, or it may be a horseshoe shaped magnet, C coil, or whatever it may be. Similarly, we have something known as electromagnet. What is that electromagnet? Basically, we are going to have a coil which is either wound over a core. Usually this core is made out of soft iron. Now when we will pass current through it, then obviously it is going to behave like a magnet. Now we will study all these things in detail in the next chapter. Now after that we will study what is known as magnetic force. Okay. Now, magnetic force is always experienced on a charge which is in motion. Unlike electric field, in case of electric field, if this is your electric field, uniform electric field, let us say, and I am going to place a positive charge over here. So what is going to happen? The electric field, as I have told you in the class, that it is going to move in the same direction as the direction of the electric field, if this charge is positive. Similarly, if this charge is negative, it is going to move against the direction of the electric field in this manner. But in case of magnetic field, suppose I am going to have a uniform magnetic field like this, and I am going to place a positive or a negative charge over here, stagnant. These are two stationary charges. Then obviously there will be no movement. So when there will be no movement, obviously it is quite sure that your force acting on these charges is going to be zero. So always remember that the most important thing is that magnetic force does not act on a stationary charge. It does not act on a stationary charge. But if there is a charge which is moving, magnetic force on a moving charge. Now here we will study different cases. magnetic force on a moving charge. So what happens? Suppose there is a magnetic field over here, and I am going to move a charge. Suppose this is a positive charge, and I am going to move this charge parallel to the direction of the magnetic field. Then also the magnetic force acting on it will also be equal to 0. So here we will suppose this is subcase A. So a moving charge inside a magnetic field which is moving in the direction parallel to that of the magnetic field is going to experience no force. So we will say that a charge moving in the direction parallel to the direction of magnetic field B vector, then your magnetic force Fm vector is also going to be equal to 0. But if I am going to have a uniform magnetic field like this, let us say I am going to have a uniform magnetic field B vector like this, and I am going to place a moving charge Q over here, which is, let us say, is moving at some angle, moving at a velocity constant speed, or rather we'll say moving with a velocity v vector, which is making an angle phi, then obviously your Fm vector modulus is given by QVB sine phi. Okay. Now, every time I have told you, whenever there is a, as you know that your force, magnetic force is a vector quantity. So whenever there is a vector quantity and it has, the expression has a sign term, then the most important thing is the direction of this phi. Okay. So always remember that this phi is the angle, between v vector towards B vector through the smaller of the two angles, through the smaller of the two angles. Because you can see over here B vector is there and G vector is there. This is one angle, the other angle is this one. Okay. That is 360 degree minus phi. Now in this case, out of these two angles, we have to take the smaller of the two angles. And secondly, always remember that this phi is directed from V vector towards B vector. If it is the opposite, that means we are going to have the angle from B vector to V vector, then obviously it is going to be a negative. Okay. So your Fm vector can be represented as QVB sine phi, because as you can see over here, if this one is directed over here, then obviously this one is going to be V sine phi. Now, obviously, this is the magnitude part, and your magnetic force is a vector quantity. So, we must add a unit vector in which is going to represent the direction of the magnetic force. So, this is your magnitude part, magnitude of magnetic force, and this one represents the unit vector in the direction of Fm vector. Now the question is, what is the direction of Fm vector? Now before that, let me write it in another form, in vectorial form as F vector is equal to. Now obviously, V and B both are vector quantities, whereas your Q is a scalar quantity. So we can write it in this manner, V vector cross B vector. Okay. So this is one expression, this is another expression. Now, if I will write B vector cross V vector, then this expression is going to be wrong. So always remember that V vector will be written first, followed by B vector. Okay. So this is the expression. Now, suppose now this time we have to find what is the direction of this Fm vector. Suppose this is a uniform magnetic field like this. I have a charge, positive charge over here, which is, let us say, directed in this direction. B vector is directed in this manner. That means B vector is over here, and the angle phi over here is equal to 90 degree. So always remember that, as we have learned previously, that your cross product results in another vector quantity whose direction is always directed perpendicular to the plane which contains both the vectors. In this case, it is V vector and B vector. So obviously, suppose let us say this is your x-axis and this is your y-axis, then obviously this one will be z-axis, and in this case V vector and your B vector are in the xy plane. So obviously your Fm vector will be perpendicular to the plane xy, and in this case your Fm vector will be directed along the z-axis. That means perpendicular to both B vector and V vector. So in this way we used to find the direction. Now let us write this equation in a little bit modified manner. Why we need to write it in a modified manner? Because this expression, either this expression or this expression, these two expressions are dealing with a single charge, So when we are dealing with a charge, these two equations stands good. But if there is a stream of charge flowing through a conductor, that means when a conductor is carrying a current, then this expression will be not of much use, and rather we will write this as Vm vector is equal to Q modulus V B sin phi a cap, and over here we can write this as Fm vector modulus is equal to modulus of Q V B perpendicular. That means this one will be replaced by a expression B perpendicular, and B perpendicular is equal to B sin phi. So this is another way of writing this force, magnetic force expression. Now this equation is particularly suitable for conductors carrying current. We'll talk about it later on. Now, till now we have been talking about magnetic field, and it is represented by B vector. Okay, let me give some idea about this B vector. B vector, the unit of this B vector is known as Tesla. In the honor of Nikola Tesla. So usually it is represented by the symbol T. Do you know your Earth is also a big magnet? So if we will talk about the Earth's magnetic field strength, Earth's magnetic field B vector is equal to 10 to the power minus 4 Tesla, or this can sometimes also be written as 1 Gauss. So 1 Gauss is equal to 10 to the power minus 4 Tesla. Okay. Now, another way by which we can, okay, in the previous case we have been talking about this Fm vector. Here we have taken this as positive sign, or the charge was positive. Now suppose let us replace this charge with a negative one. Then how we are going to find the direction? Okay. Rather, I will say, let me tell you another method by which you can easily find the direction of any sort of charge, of any polarity, whether it is positive or negative. Okay. So first talk about this positive charge. For positive charge, suppose let us say this is the direction of the magnetic field. Let us say this is the direction of V vector. V vector is obviously making an smaller angle phi over here. Then obviously, suppose this is your plus Q, then your force F M vector is directed in this way, perpendicular to the plane containing both V and B. Now, obviously, in this case, Fm vector can be directed in this way, as well as it can also be directed in this way. The question will arise. Now, why the question will arise? Because this is also perpendicular to the plane containing the two vectors. Now, how to pinpointly say which is the correct direction? For that, we will make use of something known as a right hand thumbs rule. What is this rule? Very simple rule. First step. First, we will curl our fingers in the direction of V vector. Okay, let me show you. Suppose, let us say, this is your V vector. So all my fingers, as you can see, all my 4 fingers are directed in the direction of V vector. Now, second step is I will curl my fingers in the direction towards B vector. So I will turn my, or I will curl my 4 fingers in the direction towards B vector through the smaller of the 2 angles. Now, if this is the case, then you can see my thumb is pointing upwards. So this finger is going to represent or going to give you the direction of the magnetic force. So first step is curl your fingers along V, rather I will say put your fingers along V vector direction or direction of V vector, as you can say. Second, curl the fingers from V vector towards B vector. Third step, towards B vector through the smaller of the 2 angles. Third step, put the fingers of right hand. Okay, this is important. Right hand along V vector. Call the fingers of right hand, RH I am writing, from V vector towards B vector through the smaller of the 2 angles. Now, the thumb of the right hand represents the direction of the magnetic force Fm vector. Okay, so this is for a positive charge. Similarly, suppose I want to find it for negative charge. This is quite simple. If you understand how to find the direction of Fm vector for a positive charge, then finding the direction for negative charge is quite easy. Now, in this case, let us say this is the direction of the B vector. Let us say this is the direction of B vector. This angle phi is the smaller of the 2 angles. But here there is a negative charge over here. Then how to find the direction? First 2 procedures. First is consider the charge to be a positive charge. Very simple way I am telling you. Consider the charge to be a positive charge. Assume it. Then find the direction. Find the direction of FM vector using right hand thumb rule. Right hand thumb rule. Okay? Using right hand thumb rule. Third, this is the most important step. The direction of magnetic force on the negative charge, negative moving charge, is just opposite to the direction of the thumb. So in this case, suppose I will consider this to be a positive charge. Obviously, it is going to be in this direction, FM vector. But since it is negative charge, and as per our procedure, the direction will be just opposite to that of your, in the case of positive charge. So your FM vector will be directed in this manner. So this is how you are going to find the direction for both positive charge and negative charge. Now let us consider one example. Suppose let us say this is your B vector. This is your V vector. Okay. Now this is, let us say, a positive charge. Now obviously how to find the direction? Now the first step is curl the fingers of your right hand. This is my right hand. I'll place the fingers along the direction of V vector and try to move it in the direction towards B vector through the smaller of the two angles. This is the smaller of the two angles, phi. Obviously in this case, as you can see, so it is along V vector. I will curl the fingers and my thumb is directing downwards. So obviously the direction of your FM vector will be directed into the paper, right? So this is how you are going to find the direction of FM vector. Okay, so in the next video we'll talk about magnetic flux.
Was the video okay for you all? Yes?
Yes, sir.
Okay.
Yes, sir.
So, do you gain anything from that? Just having a glimpse of what I need to tell you during our regular classes? Yes?
Yes, sir.
Okay, fine. So, let us move on for the next video. Next video will start at 3 o'clock. So, let us have a break for 5 or 6 minutes. Okay, then we will start with our other video. Fine.
Okay, sir.
Okay, students. Right now, I am going to make another video, and the same chapter, that is chapter number 27, is still continuing. This is my 10th video, I suppose. Over here, we are going to study about magnetic field lines and magnetic flux. So, we have already our electric field lines, and in case of electric field lines, suppose there is a single point charge like a plus positively charged body or a single positive charge, then these are the electric field lines. So it has a positive divergence. That means the electric field lines used to start from the center of the positively charged body, and they used to move, or rather I will say radiate out in this manner. Similarly, if I have a negative charge, then these electric field lines are going to converge towards the center of this negative charge. And if I will bring these two charges close to each other, then obviously the electric field lines will be bending like this. And you all know that this is how it is going to look like. Now, we will talk about the magnetic field lines. Okay. So, let us first consider a very simple magnet, that is your bar magnet with a north and south pole. As I have already stated, that unlike electric field, I cannot have an isolated north pole or an isolated south pole. They always comes in pair. It is impossible to have a magnet with a single pole, maybe it is a north pole or a south pole. It is not possible to have. Now the magnetic field lines will be looking something like this. It will start from the north pole and it will be terminating at the south pole like this. So this is how the electric field lines are going to start from the north pole and they used to terminate at the south pole. So this is how it is going to look like. And inside the magnetic specimen, these magnetic field lines will also be traveling, or will start from the north pole and it will be ending at the south pole. So these lines which I am drawing, they are moving towards infinite. Okay. So what are the similarities between the two lines? First one, both in case of electric field and magnetic field, your magnetic field lines will start from north pole and terminate at south pole. Okay. Similarly, in case of electric field lines, they will start from the positive charge and they will be terminating at the negative charge. Another important similarity between these two lines is that in case of electric field lines, the lines of electric field, they don't intersect each other. Similarly, in case of your magnetic field lines, they don't intersect each other. But there is a very big or important difference between the electric field lines and magnetic field lines. What is that? Electric field lines, they are sometimes also known as electric lines of force. Electric lines of force. But in case of magnetic field lines are not same as magnetic lines of force. Okay. So this is a very, very important thing that we need to remember, and this is the major difference between both of them. Electric field lines are also known as electric lines of forces. It is because any point on these electric field lines is going to indicate the direction, or any point on this electric field lines, the tangent at that point is going to indicate the direction of the electric force that is going to be experienced by a charged particle. For example, as we have already studied, suppose this is a positive charge and this is a negative charge, and let us say these are the electric field lines. Okay, these are the electric field lines. Okay, so it is moving in this manner, moving out, radiating out. So let us say this is the case of an electric field line, and suppose at this point P, I will draw a tangent. You can see if I am going to place a particle over here, then the particle will be experiencing a force. Let us say F, suppose I will place a positive charge, it will be facing a force Fe, which is equal to QE, and the direction is indicated by the direction of this tangent. But unlike your electric field, magnetic fields are not like that. In case of magnetic field, as I have already told you how to find the direction of the magnetic force on a particle, charged particle. And of course, the another important thing is that the charged particle must be moving. It must be in motion. If it is stationary, then there will be no magnetic force that is going to be experienced by it. Because you all know your F vector is equal to Q, V vector cross B vector. Now, if V vector is equal to 0, then obviously your M vector is also equal to 0. Similarly, if V vector is parallel to B vector, then what is going to happen? Your phi, that is the angle between your V vector directed towards the P vector, is going to be equal to 0 degree. So ultimately, your sin phi is going to be 0 degree, and also your Fm vector is also going to be equal to 0. So these are the major differences between the two lines. Okay, now we will talk about magnetic flux. Similarly, we have already talked about electric flux. Now we will talk about magnetic flux. And the definition is quite the same. The magnetic flux is represented by a symbol phi m. And obviously, as you know that electric flux is a scalar quantity, similarly, your magnetic flux is also going to be a scalar quantity. And it is given by the flux passing through a unit area held perpendicular to the field. Now, the unit is given by Tesla per meter square, or in other words, we can simply say it as Weber, WB. Now, let us talk about this magnetic flux in detail. First case, suppose let us say this is the magnetic field. It is a uniform magnetic field, and I am holding a unit area perpendicular to this magnetic field. Now, how to ascertain that this is perpendicular? Always remember that suppose this is a plane, then its area vector, A vector, must be parallel to that of your B vector. So in this case, your phi m is given by B into A. Now, obviously, B is a vector, A is also a vector, and since phi m is a scalar quantity, it must be a dot product. So in this way, we are going to evaluate the magnetic flux for a uniform magnetic field with a unit area held perpendicular to it. Now, suppose let us say the field is at some angle phi. Again, this is a uniform electric field, and this electric field is making some angle phi. This is your A vector, and let us say this angle is equal to phi. Okay. Now, in this case, your phi m must be equal to the component of your B vector along your A vector. So in this case, suppose this is your B vector, and let us say this is your A vector, and the angle between them. Obviously, over here, we are not concerned about the direction of this angle, because it is not going to contain a sine term, as you will be seeing after some time. Now, as I told you that this B component, the component of B along the direction of A vector. So in this case, it is coming as B cos phi A. Now, if I will make a little bit of rearrangement in the terms, I can write it as BA cos phi. Now, this is a quite a familiar term. B being a vector and A being a vector, your phi m can also be written as B vector dot A vector. So, in this case, you are getting this figure. Now, if it is inclined at some angle, I can also write it in this manner, where phi is the angle between B and A, and we are not concerned from which direction the angle phi is directed, because this is basically containing a cos term, and cos of minus phi is also same as cos phi. Now let us talk about a non-uniform electric field. Suppose let us say this is a non-uniform electric field, and I am having a area like this. Okay. Now in this case, the magnetic field is not uniform. So in this case, we write it as phi m is equal to, let's say this is case 3, and case 3 is the generalized case. Generalized case. Now, your phi m is given by P vector dot dA vector surface integral A, or simply we can write it as ds also. So this is actually the most generalized formula for finding the magnetic flux. Now if the field is uniform, this formula can again be applied in order to find it. If the field is non-uniform also, we can use the same formula or expression in order to find the value of phi m. Okay. Okay. Now, with some idea about the magnetic flux, now we will move on to Gauss law for magnetism. Now, in case of electric field, we have studied about this electric flux, and after that only we talked about this Gauss law for electric field. Now we'll talk about Gauss law for magnetic field, or simply we can tell it as Gauss law for magnetism. So just have a recall of what we have studied for electric field, Gauss law. The Gauss law was saying that the total flux coming out of a closed surface is equal, or rather will say proportional to the amount of charge that was enclosed by the closed surface. Okay, and over there we were writing that your phi E is equal to Q enclosed by epsilon. So this is your Gauss law, which is also equal to E vector dot ds vector closed surface integral. So this is what was your Gauss law for electric field. Now we will talk about the Gauss law for magnetic field. Now your Gauss law for magnetic field is given by this phi m is equal to 0 for a closed surface integral. What does that mean? That means your closed surface integral of B vector dot dA vector, B vector dot dA vector is equal to 0. Now the question is why it is equal to 0. Why in the previous case it was not equal to 0, in this case it is equal to 0. Now let us say, suppose I will say that this is the north pole, this is the south pole. So these are the electric magnetic field lines that are coming out of it, and this is what is going towards it. Now if I enclose it in a closed surface, you can see the total amount of flux that is entering is equal to the total amount of flux that is coming out. So in this way we can explain that in a very simple manner, that your closed surface integral of B vector dot dA vector is equal to 0. So this is known as Gauss law for
magnetic field. So this is the major difference between them. In case of electric field, phi E is equal to Q enclosed by epsilon is equal to closed surface integral E vector dot ds vector, or rather we can say, we can also write it as dA vector, doesn't matter. Approach is said. In case of your magnetic field, your Gauss law is given by closed surface integral of B vector dot dA vector, and it is equal to 0. In the next video, we will talk about the motion of charged particle in a magnetic field. Thank you. Is my voice audible to you all?
Yes, sir.
Okay, so there are some questions that you have mentioned, whether there will be practical exam at the end of the examination semester. Obviously, there will be. I'm quite sure about that. Now, the only thing that I can help you out is that I'll send you the copies of the lab manual. If possible, go through those manuals, and most probably three experiments we have shown you. One on meter base, the other one is the RLC experiment, and the third one is that regarding the change of magnetic field with respect to the current. So these three has already been covered, and most probably we will concentrate on only these three experiments. Obviously, I'll talk to my coordinator, and I'll convey that you people are inquiring about this problem, and whatever message or whatever information he conveys me, I will convey it to you all. Okay, so don't worry about that. We are having this lab quite after some time, maybe around 1 month ahead. So before that only, I'll take the responsibility of taking care of your lab. So don't worry about that. Unless and until I have some videos with me in order to play it, I just cannot waste this practical class. So it is better we will go through these types of videos, and whenever any information regarding the practical comes, I'll definitely communicate it to you. Okay. So we'll end our class over here. So let us meet on Monday. So for the timing, let us stop the class over here. Is there anything you want to ask me? Yes, anybody? Okay, so we'll stop the class over here. Thank you.
Thank you, sir.
Okay, my pleasure.